AI mistakes are not anomalies. They are an expected outcome of how learning systems operate. This video explains why AI errors occur, focusing on data, model design, and deployment factors rather than sensational failures or intent. AI systems are probabilistic tools. Because they estimate likelihoods rather than truths, mistakes are unavoidable even under ideal conditions. AI learns exclusively from examples. If examples are limited, misleading, or incomplete, errors will reflect those limitations. A model can only learn from what it is shown. Missing data creates blind spots that cannot be corrected through computation alone. Incomplete datasets leave gaps in coverage. When real-world inputs fall into those gaps, predictions degrade. Bias emerges when training data reflects historical or social imbalances. Models reproduce those patterns without awareness. Noise refers to errors, inconsistencies, or inaccuracies in data. Noise weakens learning signals and increases uncertainty. Labels are often created by humans. Human judgment introduces subjectivity, disagreement, and inconsistency. Some concepts lack clear ground truth. When labels are ambiguous, models inherit that ambiguity. Small datasets limit diversity. Without variation, models fail to generalize beyond narrow cases. Distribution shift occurs when real-world conditions differ from training conditions. Models struggle outside familiar patterns. Human behavior and environments change over time. Static models cannot adapt automatically. Edge cases are rare situations poorly represented in data. Models perform worst precisely where coverage is weakest. Overgeneralization occurs when broad patterns mask important distinctions. Simplified models cannot capture full complexity. Abstraction trades realism for tractability. Every model assumes a simplified version of reality. Those assumptions constrain behavior. AI optimizes specific objectives. Anything not captured in that objective is ignored. Optimizing proxies rather than real goals creates misalignment between outcomes and intentions. Trade-offs are unavoidable. Improving one metric often worsens another. Overfitting occurs when models memorize training data rather than learning general patterns. Underfitting happens when models are too simple to capture structure. Hyperparameters influence learning dynamics. Poor choices degrade performance. Random initialization introduces variability. Identical training runs can produce different results. Training processes can be unstable, especially in complex models. Hardware limitations introduce numerical approximations that affect outcomes. Model size reflects trade-offs between capacity and resources. Opaque models limit insight into reasoning, complicating debugging. Confidence calibration errors mislead users about reliability. Overtrust leads humans to defer judgment inappropriately. Undertrust prevents beneficial assistance from being used. Deployment contexts introduce complexity absent from training environments. Feedback loops can reinforce errors if unchecked. Without monitoring, degradation goes unnoticed. Delayed updates allow models to drift from reality. Integration with other systems introduces new failure modes. Data leakage contaminates evaluation, overstating performance. Evaluation metrics capture only part of system behavior. Using the wrong metric creates false confidence. Human design choices embed assumptions into systems. AI lacks common sense. It cannot reason beyond patterns. Correlation is not causation. AI cannot infer causes. Adversarial inputs exploit model weaknesses intentionally. Security risks arise from system openness and scale. Scaling magnifies small errors into systemic problems. Failures can cascade across interconnected systems. Errors persist because elimination is costly and complex. The goal is risk reduction, not perfection. Human oversight mitigates unavoidable limitations. Responsible expectations align capability with reality. Next, we explain overfitting and underfitting intuitively.